There is a place in space where the very concept of cold is rewritten. The Boomerang Nebula is the coldest known region in the entire observable universe, a cosmic expanse chilled to just 1 degree above absolute zero. By the end of this journey, you will understand how this profound cold challenges the fundamental laws of physics and reshapes our story of stellar life and death. We will uncover what violent process created this deep freeze and explore the strange quantum behaviors that emerge when matter nearly stops moving entirely. What do you believe is the ultimate limit of cold in our cosmos? Absolute zero is the ultimate cold, a theoretical floor at -273.15 degrees Celsius, where the very jiggling of atoms almost completely stops. Picture the deepest cold you have ever felt, a frigid winter day or the chill from an open freezer. That is nothing. At absolute zero, matter enters a state so still, so devoid of energy, that it defies our everyday experience. The Boomerang Nebula exists a single, fragile degree above this impossible baseline. To put that into perspective, even the empty void of space is not truly empty. It is filled with the faint, leftover warmth of the Big Bang, a relic glow called the cosmic microwave background. That background radiation measures a toasty 2.7 Kelvin. The Boomerang Nebula is colder than the afterglow of creation itself. This is not merely a record-breaking statistic. It is a profound cosmic anomaly that forces us to rethink the rules of energy and disorder. How can a place in space become colder than the universe's own background temperature? What strange engine is powerful enough to drain away so much heat? Understanding this foundational chill is the first step into the nebula's silent, frozen heart, a realm where the normal rules of physics begin to fray at the edges. Its symmetrical shape appeared in telescope data as early as 1980, a faint and puzzling object in the southern sky. Astronomers initially classified it as a planetary nebula, a common enough final act for a dying star. But this was no ordinary stellar farewell. The name Boomerang Nebula came from those early, ground-based images, which showed a lopsided, bow tie-like structure that reminded scientists of a returning throw. For over a decade, its true identity remained hidden, its most shocking secret locked away. The pivotal moment arrived with the Hubble Space Telescope in the 1990s. Hubble's sharp vision cut through the ambiguity, revealing an intricate, hourglass-like structure of glowing gas and dust, far more complex than anyone had guessed. Yet its beautiful form was not its most astounding feature. Using powerful radio telescopes, researchers then measured its temperature. The data was unequivocal. The expanding gases within the nebula were chilled to a mere 1 degree above absolute zero, making it the coldest natural place ever found. This was the moment of true discovery. It proved that the universe could spontaneously create a deep freeze more intense than the void between galaxies. The identification of the Boomerang Nebula stands as a testament to our growing technological reach. Without these advanced eyes in the sky, its profound cold would have remained an invisible whisper in the dark. This revelation forces a simple, humbling question. What other cosmic extremes are hiding in plain sight, waiting for the right tool to uncover them? To truly grasp this anomaly, we must first find it in the vastness. Nestled within the constellation Centaurus, a staggering 5,000 light-years from Earth, this cosmic icebox presents a formidable challenge to our curiosity. Its faint glow and minuscule apparent size mean it barely registers against the backdrop of space, a whisper of cold in a silent night. To listen to that whisper, astronomers cannot rely on a single eye in the sky. They must combine the powers of different telescopes, each sensitive to a different kind of light. Optical telescopes capture its ghostly shape, while infrared instruments peer through its dust to sense warmth we cannot see. But it is the advanced radio telescopes, like the Atacama Large Millimeter Array in Chile, that have truly pierced its veil. Ulma network of dishes acts like a single, colossal eye, resolving intricate details of the nebula's gas and dust with stunning precision. The data from these observations tells a story of violent motion. The gas you see billowing out from the central star is not drifting lazily. It is racing outward at over 164,000 kilometers per hour. This breakneck expansion is the very engine of its cold. Think of the air rushing out of a spray can. As the gas expands rapidly into the vacuum of space, it does work, using up its own internal energy. This process, called adiabatic expansion, is like the universe's most powerful air conditioner, actively draining the heat from the nebula's heart and leaving it colder than the space around it. By dissecting the light that filters through this expanding cloud, scientists can read its secrets. They analyze its spectrum, looking for subtle shifts and dips that reveal not just its composition, but its temperature and velocity. This is how we know the precise, bone-chilling numbers. Every new observation, every data point from this remote outpost is a piece of a puzzle. It forces us to use our ingenuity to study a place we can never visit directly, mapping its position not just in the sky, but in the grand, swirling story of our own galaxy. That faint absorption of background radiation was the crucial clue. In the early 2000s, radio astronomers pointed their dishes toward the Boomerang Nebula and detected a specific, telltale signature from carbon monoxide molecules drifting within its expanse. These molecules were not glowing with their own energy. Instead, they were acting like a cosmic sponge, soaking up the faint, pervasive warmth of the cosmic microwave background. For this to happen, the gas itself had to be colder than the background radiation. The math was inescapable, pointing to a temperature of just about 1 Kelvin. This was the definitive proof. The nebula was not just a little bit cold. It was the coldest natural place ever measured, a title it still holds today. The explanation for this profound chill lay in the nebula's own violent motion. The central star is ejecting its outer layers at a staggering speed of over 150 kilometers per second. This is the key to the entire mystery. When a gas expands that quickly into the near vacuum of space, it behaves exactly like the compressed air rushing out of a spray can. As the gas expands, it has to push against the nothingness around it, and that act of pushing requires energy. The only energy it has to spend is its own internal heat. So, as it billows outward, it uses up that thermal energy, growing colder and colder in the process. Scientists call this adiabatic cooling, the very same principle that powers the refrigerator in your kitchen. This discovery did more than just confirm a record. It revealed that a star's death can forge pockets of extreme cold, a paradox that upended simpler models of stellar evolution. The violent end of a sun-like object can, through a specific and rapid process, create the ultimate deep freeze. With the engine of its cold now understood, our attention turns to the intricate structure sculpted by this furious expansion. What ghostly architecture has this process left behind? This ghostly hourglass shape is not a static sculpture but a testament to violent, ongoing creation. The nebula's bipolar structure, with two vast lobes of gas expanding from a central point, forms its iconic silhouette. These lobes are not filled with simple, uniform gas. They are a complex soup of molecular hydrogen, carbon monoxide, and microscopic dust particles, each component playing a vital role in the great cosmic chill. The dust, in particular, acts like a network of tiny radiators, helping to carry thermal energy away as the gas expands. At the very heart of this system lies the engine itself, a dying red giant star. This is not the brilliant, stable sun we know. It is a swollen, aging star in its final throes, blasting its own outer layers into the void with intense, relentless stellar winds. These winds are the sculpting force, carving out the lobes and driving the entire expansion process. But if you could fly through one of those lobes, you would find it is far from smooth. Observations reveal a chaotic interior with clumps and streams of denser gas moving at slightly different speeds. This intricate anatomy is crucial to understanding the profound cold. A perfectly smooth, uniform expansion would not cool as efficiently. It is the complex, turbulent structure, with its varying densities and pathways, that allows the heat to dissipate so rapidly and completely. The nebula's beautiful form is directly tied to its function as a deep freeze. This intricate structure raises a deeper question about the star that forged it. What kind of stellar death throes are powerful enough to craft such an elaborate and frigid tomb? These stellar winds are a hurricane of matter and energy. Pouring from the central red giant star, they flow at supersonic speeds, a relentless gale that carries the star's own substance out into the void. This is not a gentle breeze but a fundamental force of ejection, stripping away mass and energy on a colossal scale. It is this very process of violent mass loss that directly powers the nebula's great expansion and, in turn, its profound cooling. The faster and more massive the wind, the more dramatic the resulting deep freeze becomes. For a long time, astronomers assumed this outflow was symmetrical, a uniform bubble blowing into space, but spectral analysis in the 2010s revealed a far more dynamic and uneven reality. The data showed a clear asymmetry, with one lobe of the nebula expanding significantly faster than its counterpart. This imbalance is not a minor detail. It fundamentally affects the temperature distribution within the nebula, creating pockets of even more intense cold where the expansion is most rapid. This discovery of lopsided winds forced a major rethink. What could possibly cause such a beautifully symmetrical structure to form from such an uneven process? The leading theories point to two compelling possibilities. The dying star at the heart of it all might not be alone. A binary companion, a second star orbiting close by, could gravitationally tug at the outflow, channeling the wind and creating the observed imbalance. Alternatively, powerful magnetic fields generated by the star itself could act as invisible guides, funneling the stellar wind into two opposing jets with slightly different forces. This finding transforms our view of the nebula from a simple, expanding cloud into a complex system, shaped by hidden interactions at its core. The impact of these winds provides a stunning model for how stellar activity, even in its final acts, can forge the most extreme environments in the cosmos. It connects the intimate death throes of a single star to the vast, ghostly structures we see light years away. The story of this cold does not end with the winds themselves, however. It forces us to look even closer at the nature of the star that produces them. What strange and ancient sun could unleash such a perfectly calibrated storm? The star at the center of this cosmic icebox is a dying sun. It is currently caught in a brief, violent transition, shedding its vast outer layers to reveal a dense, fading core. This process transforms it from a bloated red giant into a future white dwarf, a stellar ember that will slowly cool over billions of years. The sheer rate of this transformation is staggering. The star is losing mass at an incredible pace, ejecting material equivalent to the mass of our own Sun every 1,000 years. This torrent of gas is the raw substance of the nebula itself, the very fabric of the ghostly hourglass we see from Earth. Its surface temperature and immense luminosity are the power sources for the stellar winds. The star's intense radiation pushes on the escaping gas, accelerating it to the supersonic speeds that drive the nebula's rapid expansion and, consequently, its record-breaking cold. What makes this engine particularly fascinating is its relative youth. In stellar terms, this is a very new planetary nebula. Its central star has only just begun this final phase, which means its winds are at their most powerful and its mass loss is at its most dramatic. This youthful intensity is likely the primary reason the Boomerang Nebula is so much colder than any other known object. By studying this central engine, astronomers can project the nebula's future. Over the next several thousand years, as the star completes its transformation into a white dwarf, its winds will gradually weaken, the furious expansion will slow, and the nebula's delicate structure will begin to dissipate, its gases slowly mixing with the interstellar medium. This entire system, from the central star to the farthest reaches of its frozen lobes, is a single, interconnected event. It demonstrates how the death of one star is not merely an end, but a process that can forge the most extreme and fleeting environments in the galaxy. This leads us to a broader cosmic question about the fate of all such stellar structures. What happens when this deep freeze finally ends? The nebula's perfect hourglass shape is an illusion. Recent high-resolution observations have torn it away, revealing a deep and fundamental flaw in its symmetry. One of the vast lobes stretches further into space than its twin, a lopsided expansion that creates a distinct temperature imbalance. The more extended lobe is measurably colder, a detail that shatters the simplest models of how these structures form. This is not a minor imperfection. It is a vital clue pointing to powerful external forces shaping the star's final breath. What could possibly reach into this system and pull one side of the nebula into a colder, more extended state? Astronomers point to two invisible suspects. The first is the thin soup of interstellar material that the nebula is expanding into. If this background gas is not perfectly uniform, it can act like a gentle but persistent headwind, resisting one lobe more than the other and distorting the entire outflow. The second, and perhaps more compelling, force is magnetic. Studies using a technique called polarimetry have detected the subtle signature of dust grains within the nebula, all aligning in specific, organized directions. This is a telltale sign of an underlying magnetic field at work. These invisible lines of force could be channeling the outflowing gas, acting like celestial rails that guide the stellar wind and create the observed asymmetry. This discovery fundamentally changes our view of planetary nebulae. They are not isolated, self-contained events. Their beautiful and often complex forms are a dialogue between the dying star's violent ejections and the subtle, pervasive influences of its galactic environment. This cosmic tug-of-war does more than just alter the nebula's shape. It directly influences the very engine of its cold. The lopsided expansion means one lobe is doing more work, expanding more rapidly against the vacuum, and thus cooling more efficiently than the other. This irregularity fine-tunes the entire system, creating pockets of ultra-cold gas that push the limits of physics. It forces us to ask what other beautiful cosmic structures are being sculpted by forces we cannot directly see. The nebula's profound cold is not the result of a single process, but a symphony of chilling mechanisms working in perfect concert. At the heart of it all is adiabatic expansion, the same principle that chills the air from a spray can. Here, the gas billowing from the dying star expands into the near-perfect vacuum of space so rapidly that it cannot hold onto its own heat. The energy required for this explosive growth is stolen directly from the gas's internal thermal motion, causing its temperature to plummet dramatically. This is the primary engine of the deep freeze, but it does not work alone. As the gas cools, a second, more subtle process kicks in. Molecules of carbon monoxide and molecular hydrogen within the cloud begin to act like microscopic radiators. They vibrate and rotate at specific frequencies, shedding their remaining energy by emitting faint beams of infrared light that travel unimpeded out into the darkness of space. This molecular cooling continuously drains more warmth from the system. Adding a final layer to this chilling effect are countless microscopic dust grains. These tiny particles absorb the star's visible light and re-radiate it as lower-energy infrared radiation, effectively acting as a heat exchange system that further strips thermal energy from the gas. Together, these processes create a powerful feedback loop. The expansion cools the gas, which allows the molecules and dust to radiate energy away more efficiently, which in turn makes the gas even colder. This self-reinforcing cycle is so effective that it maintains the nebula's extreme temperature, creating a pocket of cold that defies the warmer space around it. Scientists studying these natural refrigeration methods have applied the same principles here on Earth. The laser cooling techniques used to create Bose-Einstein condensates in laboratories operate on a similar idea of using radiation to strip energy from atoms, bringing them to within a fraction of a degree of absolute zero. The Boomerang Nebula is a cosmic demonstration of the ultimate limits of cold, a natural laboratory that challenges our understanding of how matter behaves when it nearly stops moving entirely. How does this incredible deep freeze compare to other cold spots scattered throughout the cosmos? The Boomerang Nebula may hold the record, but it is not alone in the cosmic deep freeze. Across the galaxy, other regions flirt with profound cold, yet none have crossed the same threshold. Take the vast emptiness of the Boötes void, for instance. This enormous, sparsely populated region of space has an average temperature that hovers just above the cosmic microwave background, chilled by its own lack of stars and energy sources. But this is a passive cold born from absence. There is no active engine there, no violent process actively draining heat to create a chill deeper than the void itself. Even within more dynamic structures like the Crab Nebula, we find pockets of intense cold. The powerful pulsar at its heart blows a fierce wind of particles, which can create localized cold spots through rapid expansion. Yet these are small, transient features within a much hotter cloud, unable to achieve the nebula's widespread, stable deep freeze. Data from satellites like Planck confirm that large cosmic voids can approach similar baseline temperatures, but they are simply empty space cooling naturally. The Boomerang Nebula is different. Its cold is an active, ongoing achievement. These comparisons are crucial. They show us that extreme cold is not just about a low number on a thermometer. It is about the process that creates it. The nebula's chill is a direct, energetic consequence of a star's death throes, a perfect storm of expansion and radiation. Other cold regions are quiet and still, while the Boomerang is a silent hurricane, a place of violent motion that results in absolute stillness. This pattern tells us something fundamental about our universe. The most extreme thermal environments are not found in simple emptiness, but in the complex, energetic aftermath of stellar life. They are rare, fleeting, and tied directly to specific, catastrophic events. Recognizing this diversity forces us to ask how such a perfect storm of conditions could even be possible. What underlying laws of physics allow a dying star to build its own frozen tomb? Theoretical models allow us to peer into the heart of this silent storm. Astrophysicists build intricate digital simulations, weaving together the laws of hydrodynamics and quantum mechanics to recreate the nebula's frigid environment. They input every known variable, from the violent velocity of the expanding gas to the subtle influence of its magnetic fields and the precise density of its molecular clouds. One prominent simulation focuses on the shock front created by the central star's supersonic winds. This model suggests that as the stellar wind slams into the slower, previously ejected material, it creates a powerful boundary of compressed gas. This shock front acts like a piston, violently accelerating the outer layers of the nebula and forcing them to expand even faster. It is this supercharged expansion that drives the most intense phase of adiabatic cooling, pushing the temperature down to its record-breaking low. A competing theory adds another layer to the chill. It focuses on the process of radiative transfer, where the light from the central star interacts with specific molecules like carbon monoxide. In this model, these molecules absorb the star's energy only to immediately re-radiate it away as infrared light, which then escapes unimpeded into space. This constant one-way flow of energy acts like a bleeding wound, systematically draining the nebula's remaining warmth. These are not just abstract ideas. They are tested relentlessly against the hard data from telescopes like ALMA. When a simulation predicts a certain temperature for a specific lobe of the nebula, astronomers check it against their actual measurements. When the numbers do not match, the model is refined, the equations are tweaked, and our understanding grows sharper. This process of prediction and observation is how we move from simply seeing the cold to truly comprehending the engine that creates it. The implications of these models stretch far beyond a single nebula. They give us a crucial window into the conditions of the early universe, a time when the entire cosmos was a vast, expanding cloud not unlike the Boomerang Nebula, cooling from a hot, dense state toward the cold void we see today. By perfecting our understanding of this local deep freeze, we are effectively learning to read the thermal history of everything. How does the life cycle of this cosmic icebox unfold from this point forward? This deep freeze is a fleeting moment in cosmic time. The Boomerang Nebula is only about 1,500 years old in its current form, a mere blink in a stellar lifetime. This clock started ticking when its central star first began to violently shed its outer layers, a process that is still unfolding today. We are witnessing its youth, a period of maximum intensity where its stellar winds are strongest and its expansion is most rapid. For the next several thousand years, this ghostly structure will continue to billow outward, its gases cooling even further as they race into the void. But this is not a permanent state. The very expansion that creates its profound cold will ultimately be its undoing. As the nebula grows larger and more diffuse, its delicate structure will begin to fray. The gas will slowly mix with the thin material of interstellar space, losing its cohesive form and its record-breaking chill. Observations of older, similar nebulae suggest a final fate of near invisibility, a faint, dissipating cloud with a solitary white dwarf star glowing at its center. This entire evolutionary timeline is a crucial key for astronomers. By charting the nebula's progress from violent birth to quiet dissolution, they can piece together the life cycle of mid-sized stars with unprecedented detail. They can create models that predict how its temperature will peak and then gradually rise as the central engine fades. This historical perspective does more than just document a distant object's fate. It gives us a crystal ball into the future of our own solar system. In roughly 5 billion years, our sun will enter its own red giant phase, likely creating its own planetary nebula as it sheds its outer layers. The beautiful, frozen hourglass we see in the Boomerang Nebula is a preview of the artistic and violent end that awaits our own star. This invites a profound reflection on our place in a vast, cyclical cosmos, where the death of one star becomes a lesson for the future of another. This profound cold is far more than a cosmic curiosity. It actively tests the very laws that govern our universe. The Boomerang Nebula serves as a natural laboratory, a place where the rules of thermodynamics and quantum mechanics are pushed to their absolute limits. Here, in this deep freeze, matter behaves in ways that are impossible to replicate fully on Earth. We can observe how atoms and molecules interact when they are nearly motionless, offering a unique window into the quantum world that underlies all of reality. This is not just about breaking a temperature record. It is about using this extreme environment to question and refine our most fundamental scientific theories. The nebula's existence also rewrites the final chapter for stars like our Sun. Its rapid mass loss and the intricate structure of its outflow are now critical data points for models of stellar evolution. They show us that the death of a star is not a simple, gentle fade-out. It is a complex, often violent process that sculpts the interstellar medium and seeds it with heavy elements. The gas and dust you see billowing outward from this dying star will not be lost forever. Over millions of years, this same material, enriched by the star's nuclear furnaces, will drift through space and eventually collapse under gravity to form new stars, new planets, and perhaps even the building blocks of life elsewhere. This makes the nebula a crucial link in the great cosmic cycle of death and rebirth. By understanding how such extreme cold is created and maintained, we gain insight into the universe's grand energy balance. We learn how heat is distributed, how it flows, and how localized pockets of intense cold can persist against the warm backdrop of space itself. The principles of adiabatic cooling observed here are already influencing technology on Earth, from improving cryogenic systems that preserve biological materials to designing more efficient life support for future deep space missions. The silent, frozen heart of the Boomerang Nebula holds secrets that reach from the quantum realm to the future of human exploration. To unlock these secrets, however, we must first be certain of the numbers we are reading from across the void. The silent cold of the Boomerang Nebula does not give up its secrets easily. To truly map its frozen expanse, we have needed to build ever more sensitive eyes, instruments that can listen to the faintest whispers of heat or the lack of it. Recent advances in astronomical technology have revolutionized our view, turning this ghostly shape into a dynamic, three-dimensional object we can begin to dissect. At the forefront is a technique called interferometry. This method combines the light from multiple telescopes, creating a virtual instrument with the resolving power of a single, impossibly large dish. The Atacama Large Millimeter Array, or ALMA, uses this principle with stunning effect. By linking its dozens of radio antennas across the high Chilean desert, ALMA acts as a cosmic thermometer. It precisely maps the faint radio emissions from molecules like carbon monoxide drifting within the nebula. Each molecule acts as a tiny signal, and by analyzing the subtle shifts in its emission line, astronomers can read not just its location, but its exact velocity and, most importantly, its temperature. This has revealed intricate temperature gradients, showing that the cold is not uniform. Some streams of gas within the lobes are even colder than others, fine-tuning our understanding of the cooling engine at work. Meanwhile, in the vacuum of space, observatories like the Herschel Space Telescope have trained their infrared eyes on the nebula. Where ALMA listens to molecules, Herschel saw the faint glow of cold dust. These microscopic particles, chilled to near absolute zero, emit a specific infrared signature that tells us about their composition and their crucial role in radiating heat away into space. This combination of data is like assembling a puzzle from multiple senses. It allows scientists to construct detailed three-dimensional models of the nebula's structure, visualizing how the gas flows, where it clumps, and how the entire system expands over time. These models are no longer static pictures. They are dynamic simulations that test our theories of stellar winds and magnetic fields against hard, empirical data. The relentless improvement of these tools is shrinking the margin of error, reducing the uncertainties that once clouded our view. Every new generation of technology promises to peer deeper, perhaps even to find a pocket of gas within the nebula that dips below the 1 Kelvin mark, a new record in a place we thought we already knew. This progress in measurement is a story of human ingenuity, a reminder that our understanding of the cosmos is limited only by the tools we can build. And as our map of this frozen realm becomes ever more precise, it inevitably draws our attention outward to the space it occupies. How does this cosmic icebox interact with the vast, empty environment that surrounds it? This silent expansion is not happening in a perfect void. The Boomerang Nebula is pushing against the thin, scattered material of the interstellar medium, the sparse soup of gas and dust that fills the space between stars. This interaction is a constant, invisible battle at the frontiers of the nebula. As the nebula's own ultra-cold gas races outward, it slams into this tenuous background material, creating powerful shock waves. These shock fronts can actually heat the very edges of the interstellar medium, creating a faint, warm boundary around the deep freeze. Yet, remarkably, the nebula's heart stays profoundly cold. This is a testament to the incredible efficiency of its internal cooling processes. The adiabatic expansion and molecular radiation inside the lobes are so effective that they continuously drain heat faster than the external shocks can supply it. The interstellar medium does more than just provide a barrier. Its own density and magnetic fields actively sculpt the nebula. If the surrounding gas is slightly denser on one side, it acts like a gentle but persistent cushion, slowing the expansion of that lobe and contributing to the lopsided shape we observe. Invisible magnetic fields threading through the local space can also channel the outflowing gas, guiding it into the specific, extended forms that make the nebula so distinct. This delicate interplay is a key factor in the nebula's future. The record-breaking cold is a temporary victory. Over thousands of years, the relentless pressure from the interstellar medium will gradually slow the nebula's expansion. As the furious outward rush diminishes, the primary engine of its chill will weaken. The nebula's temperature will slowly begin to rise, its gases finally starting to equilibrate with the warmer space around it. By studying this relationship, astronomers see a perfect example of cosmic feedback. A dying star transforms its immediate environment, creating a structure that is then shaped and ultimately dissolved by that very same environment. This highlights a profound interconnectedness. The fate of this one spectacular object is tied to the subtle properties of the galactic space it inhabits. It forces us to see the nebula not as an isolated wonder, but as an integral part of the galaxy's ongoing cycle of matter and energy. This frozen cloud is far more than a cosmic oddity. It is a vital participant in the grand ecology of our galaxy, a silent but prolific seed disperser on an interstellar scale. The very gases that billow outward from its dying star are rich with heavy elements, forged over billions of years in the star's nuclear heart. Atoms of carbon and oxygen, the fundamental building blocks of rocks, air, and life itself, are being cast out into the void. This is the star's final legacy, a chemical gift to the cosmos. As the nebula expands, it acts like a celestial fertilizer spreader, mixing these newly created elements with the thin hydrogen and helium of the interstellar medium. This enriched material does not simply vanish. Over millions of years, gravity will pull these clouds together, and from this recycled cosmic compost, new stars will ignite, new planets will coalesce, and perhaps on some distant world, new possibilities for life will emerge. The profound cold of the nebula plays a surprising role in this process. In warmer environments, complex molecules are often torn apart by intense radiation. But here, in this deep freeze, the near standstill of atomic motion can act as a preservative. Delicate molecular chains, the precursors to more complex chemistry, might form and survive within these frigid lobes, sheltered from the destructive energy that would obliterate them elsewhere. This makes the Boomerang Nebula a kind of cosmic icebox, not just for cold, but for the very ingredients of future worlds. This perspective transforms a stellar death into a story of cosmic renewal. The end of one star becomes the raw material for countless new beginnings, connecting the silent, frozen fate of this single object to the vibrant, ongoing story of our galaxy's evolution. How does matter behave when it is chilled to such an extreme that this delicate chemistry can even occur? Within this profound cold, the familiar laws of physics begin to blur. At temperatures just 1 degree above absolute zero, the random jiggling of atoms slows to a near standstill, and a far stranger set of rules takes over. This is the domain of quantum mechanics, where matter behaves as both particles and waves, and the universe operates on probabilities. In the Boomerang Nebula's frozen expanse, these quantum effects are not just theoretical curiosities. They become the dominant forces shaping the behavior of matter on a grand scale. One of the most dramatic possibilities is a phenomenon known as Bose-Einstein condensation. Under normal conditions, atoms in a gas are a chaotic crowd, all jostling and bouncing at different speeds. But when cooled to within a fraction of a degree of absolute zero, a strange transformation occurs. A large group of atoms suddenly drops into the exact same quantum state, losing their individual identities and beginning to move in perfect, coordinated unison. They become a single, cohesive wave of matter, a super atom with bizarre properties. This state of matter is incredibly fragile, impossible to maintain in a typical Earth environment. But within the vast, shielded lobes of the nebula, where the background temperature is already so low and densities are perfect, pockets of gas could theoretically enter this condensate state. We cannot see this directly, but its signature might be hidden in the nebula's spectral data, in the specific ways light is absorbed and emitted by the chilled gases. Another quantum phenomenon likely at play is quantum tunneling. In our everyday world, for a chemical reaction to occur, particles need enough energy to climb over an energy barrier, like rolling a ball over a hill. But in the quantum realm, particles do not need to climb. They can simply appear on the other side of the barrier, as if they dug a tunnel straight through it. In the nebula's deep freeze, where atoms have almost no thermal energy to jump barriers, quantum tunneling could be the only way for certain chemical reactions to proceed. This allows for the formation of unique, fragile molecules that could never survive or form in the warmer, more energetic environment of interstellar space. These are not just abstract ideas. The principles being tested in this natural laboratory have direct implications for our own technology. The study of quantum states in such extreme environments informs the development of quantum computers, which rely on controlling matter at the quantum level to perform calculations impossible for classical machines. It guides the creation of new materials with exotic properties, like superconductors that can transmit electricity without any loss. The Boomerang Nebula offers a unique, large-scale view of quantum mechanics in action, a testing ground for the fundamental rules that govern all of reality. This naturally leads to a compelling comparison. If the universe can create such a profound cold, how do our own human-made laboratories on Earth measure up in this ultimate chill? Human ingenuity has created pockets of cold that dwarf even the Boomerang Nebula. In laboratories worldwide, scientists use laser cooling and magnetic traps to chill atoms to within a billionth of a degree of absolute zero. These nanokelvin temperatures are far colder than anything found in the natural cosmos, creating conditions where matter enters entirely new states. Atoms cease their chaotic dance and merge into a single quantum wave, a Bose-Einstein condensate, where they flow without friction in a bizarre state called superfluidity. These experiments have unlocked profound discoveries in quantum mechanics, revealing a hidden layer of reality. Yet for all their sophistication, these artificial deep freezes exist on a minute scale. They are confined to small vacuum chambers, and they last for only a few precious seconds before outside energy disrupts their fragile order. The Boomerang Nebula, by contrast, is a cosmic giant. Its chill, while not as extreme, is maintained across trillions of kilometers of space and has persisted for over 1,000 years. This vast, natural refrigerator offers a completely different kind of laboratory. It demonstrates how the same physical principles of expansion and radiation can operate on an epic scale and over immense timescales. We cannot replicate such a long-duration cooling process on Earth. This comparison is not about declaring a winner, but about appreciating a powerful partnership. Our tiny, fleeting labs reveal the quantum details of ultra-cold matter, while the nebula shows us how those same rules play out in the grand theater of the galaxy. It highlights the stunning achievements of our technology while humbly reminding us that the universe has been running its own experiments for eons. By bridging this gap between the artificial and the natural, we gain a complete picture of thermodynamics from the quantum world to the interstellar void. This synergy points directly toward the nebula's next great role, as a guide for future exploration and a template for what we might one day build ourselves. The silent storm of the Boomerang Nebula still guards its deepest secrets. Despite all we have learned, fundamental questions remain. We still do not know the precise strength and structure of the magnetic field sculpting its lobes, or if a hidden binary companion is truly tugging at its stellar winds. Could there be pockets within its expanse, even colder than 1 Kelvin, that our current instruments are too blunt to detect? The quest for answers is driving the next generation of astronomical missions. The James Webb Space Telescope, with its unparalleled infrared sensitivity, is poised to stare deep into this cosmic icebox. It will map the faintest thermal glows from its dust and gas, searching for spectral signatures of previously unknown cooling processes. Each new wavelength of light it captures is like adding a new sense, allowing us to perceive the nebula's intricate physics in ways we never could before. Further into the future, ambitious concepts for interstellar probes offer a tantalizing, if distant, possibility. Imagine a spacecraft centuries from now, flying directly through those frozen lobes, its instruments taking in situ readings of the temperature and composition. This would be the ultimate validation, turning remote observations into direct physical truth. Here on Earth, researchers are refining complex digital simulations, feeding them new data to forecast the nebula's evolution over the next 10,000 years. These models will predict how its structure will dissipate and how its chilling effect on the surrounding interstellar medium will ultimately fade. This relentless pursuit of knowledge does more than satisfy curiosity. The technologies developed to study such an extreme environment often find unexpected applications. Advanced cryogenic systems, radiation-resistant sensors, and sophisticated data analysis algorithms created for these cosmic questions can revolutionize fields from medicine to materials science. Understanding how a natural system maintains a deep freeze across light years could one day inform the design of habitats for long-duration space missions, or teach us how to manage energy and thermal regulation in the void. The story of the Boomerang Nebula is far from over. It is a continuing dialogue between human ingenuity and cosmic mystery, a reminder that every answer we uncover simply leads to a more profound and beautiful question. The silent, deep freeze of the Boomerang Nebula is more than a distant wonder. It is a teacher offering profound lessons for our own journey to the stars. The nebula's natural refrigeration methods, its adiabatic expansion and molecular cooling, provide a masterclass in thermal management. Engineers studying these processes can design better systems for spacecraft, creating more efficient ways to reject waste heat into the vacuum. This knowledge is vital for long-duration missions, where managing temperature is a matter of survival. The same principles could revolutionize cryogenic storage, allowing us to preserve food, medicine, or even biological samples for years on a voyage to another world. Imagine a future Mars habitat nestled in a permanently shadowed crater at the pole. Its survival will depend on managing extreme cold, a challenge the nebula has already solved on a cosmic scale. By understanding how this natural icebox maintains its temperature, we can learn to build shelters that insulate against the bitter chill of alien nights or harness the cold for power and preservation. This cosmic example forces us to confront the raw reality of space. It is not a void of uniform darkness, but a tapestry of extremes with islands of unimaginable cold and heat. Venturing into this environment requires more than courage. It demands a deep resilience, an ability to adapt our technology and ourselves to conditions that defy earthly experience. The nebula stands as both a warning and a guide. It shows us the challenges, but it also reveals the physical principles we can use to overcome them. Every new insight into its frigid heart makes us a little more prepared, a little more capable as a spacefaring civilization. This connection between a dying star and our future among the stars transforms the nebula from an object of pure science into a symbol of human aspiration. Its ghostly shape has begun to drift from the pages of scientific journals into the broader canvas of our collective imagination. Its ghostly shape has drifted from the pages of scientific journals into the broader canvas of our collective imagination. The Boomerang Nebula's unique status as the coldest known place has made it a star in documentaries and popular science articles, where its eerie, symmetrical beauty serves as a powerful symbol of cosmic extremes. Media portrayals often frame it as the universe's ultimate icebox, a place where the very laws of physics seem to pause. This portrayal does more than just share a fascinating fact. It wraps a complex astrophysical phenomenon in a cloak of relatable mystery, making the abstract nature of thermodynamics and stellar death accessible to millions. Artists, in turn, have been inspired to render its haunting hourglass form, using color and light to translate cold, hard data into visual poetry that evokes a sense of silent, profound isolation. This cultural journey from raw data to public icon is crucial. It transforms the nebula from an object of pure study into a shared story, one that sparks curiosity in a classroom, inspires a painter's brush, or becomes the central wonder in a television special. That widespread sense of wonder is not a trivial side effect. It is a powerful force that fuels support for scientific endeavor. When people feel a connection to a cosmic mystery, they become more invested in the tools that solve it, from supporting funding for space telescopes to encouraging young minds to pursue careers in science. This cycle of discovery, representation, and inspiration is how a distant cloud of gas becomes a landmark in our cultural landscape. It demonstrates that the true impact of a cosmic object is measured not only in Kelvin, but in its ability to make us look up and question our place in the universe. How does this cultural presence translate into a direct educational tool for the scientists of tomorrow? That silent, frozen hourglass floating in the void has become a gateway for young minds. In classrooms and planetariums worldwide, the Boomerang Nebula is not just a distant object of study. It is a story, a dramatic narrative that brings the most abstract principles of science to life. A teacher can write the number 1 Kelvin on a board, but that figure remains a meaningless digit until you attach it to the nebula's tail. Suddenly, students are not just memorizing the laws of thermodynamics. They are exploring a place where heat actively flees, where a dying star's final act is to build a cosmic freezer. This story transforms the equation for adiabatic expansion from a dry formula into the secret engine of the coldest place we know. It connects the quantum behavior of atoms to a visible, beautiful structure light years across. Planetarium shows immerse audiences in this journey, using virtual reality to simulate a flight through those billowing lobes. You are no longer just hearing about molecular cooling. You are surrounded by it, watching as digital representations of carbon monoxide molecules shed their energy like tiny, invisible lights blinking out into the darkness. This tangible experience makes the incredible real. For a student witnessing this, a career in science can shift from a vague notion to a concrete calling. The nebula's mystery has that power. It represents an unanswered question, a puzzle on a galactic scale, and that is a potent lure for a curious intellect. Countless astronomers and engineers first felt that spark of wonder not in a lecture hall, but under a dome, watching a simulation of a stellar death that defies all expectations of cold. This educational value underscores a deeper responsibility. The knowledge we gain from such cosmic extremes does not belong solely to research institutions. It is a human inheritance, a story that must be shared to inspire the innovators and problem solvers of tomorrow. As we push our instruments to probe deeper into these remote realms, we must also consider the ethics of our expanding reach. Our reach across the cosmos carries an invisible weight of responsibility. While the idea of a probe visiting the Boomerang Nebula remains a distant dream, the very possibility forces a difficult question. Should we ever send a craft into such a pristine environment, our mere presence would contaminate it. The heat from its engines, the subtle outgassing from its hull, even the microorganisms potentially clinging to its surface would forever alter the very natural laboratory we seek to study. This principle of planetary protection, long applied to Mars and moons with potential for life, extends to these unique cosmic regions as well. Their untouched state is their greatest scientific value, a frozen record of stellar processes we are only beginning to comprehend. Our first duty is to observe without disturbing, to ensure that our quest for knowledge does not irrevocably damage the object of our curiosity. This leads to a more immediate ethical dilemma, one grounded not in the future but in the present. The billions of dollars spent on building telescopes like the James Webb Space Telescope or the ALMA Array represent a monumental investment in pure science. Could that money be better spent addressing pressing needs here on Earth, on solving poverty, disease, or climate change? This is not a question with a simple answer. It forces a conversation about the value of knowledge for its own sake versus the urgency of terrestrial problems. The pursuit of understanding a nebula 5,000 light-years away does not directly feed the hungry, but the technological spin-offs from such research often do. The advanced imaging algorithms developed for astronomy now help in medical diagnostics. The materials science behind space telescopes leads to more efficient solar panels. The quest to understand the universe has a long and proven history of yielding unexpected, practical benefits that ripple through our society. The true ethical path lies not in choosing one over the other, but in striving for a balance where our ambition to explore the heavens walks hand in hand with our commitment to improving life on our own world. This reflection on our role as cosmic stewards sharpens our appreciation for the nebula's singular nature. How does this silent, frozen giant truly stand apart from every other record-breaking object we have found in the cosmos? Its record-breaking cold is just the beginning of its story. The Boomerang Nebula holds other, equally stunning titles that reveal a system operating at the very edge of physical extremes. Its stellar winds are a cosmic hurricane, screaming outward at speeds exceeding 164,000 kilometers per hour. This velocity is far greater than the winds from most other planetary nebulae, making it one of the fastest outflows ever recorded from a dying star. This is not a gentle breeze, it is a supersonic torrent, the raw power that carves the nebula's shape and drives its relentless expansion. This expansion rate itself is another marvel. The nebula is ballooning into space so quickly that its size increases by trillions of kilometers every single year, a growth spurt that is almost unmatched. These two records are fundamentally linked. The incredible speed of the wind is the direct cause of the breakneck expansion, and that expansion is, in turn, the primary engine of the profound cold. One extreme property fuels the others in a self-reinforcing cycle of cosmic violence. Even its beautiful form is a record holder. Despite the subtle lopsidedness we now detect, its bipolar, hourglass structure remains one of the most symmetric ever observed. This near-perfect symmetry suggests a remarkable stability and precision in the underlying forces, whether from a hidden companion star or an intensely ordered magnetic field, that have guided this chaotic process. What rare ingredients could survive within such a perfectly calibrated storm? Inside its frozen lobes, shielded by the pervasive cold, exists a chemical sanctuary. The nebula's composition includes fragile molecules and rare isotopes that are typically torn apart by the intense radiation found in warmer stellar environments. Here, the deep freeze acts as a preservative, allowing these delicate molecular chains to form and endure. This gives astronomers a unique window into chemical processes that are usually invisible to us, a snapshot of interstellar chemistry in suspended animation. Each of these additional records adds a new dimension to our understanding. The nebula is not a one-note wonder defined solely by its temperature. It is a multifaceted cosmic gem where extreme speed, perfect symmetry, and unique chemistry all converge. This holistic view reveals a fundamental truth about the universe. Extreme properties rarely exist in isolation. They cluster together, each one amplifying and explaining the others, creating objects that defy simple classification. How does such a confluence of extremes force us to rethink our fundamental theories of how stars die? This cosmic deep freeze is actively dismantling old certainties about how stars die. For decades, the prevailing theory of planetary nebula formation was a relatively simple one. It envisioned a slow, gentle shedding of a star's outer layers, resulting in a roughly spherical cloud that would glow warmly from the exposed stellar core. The Boomerang Nebula shatters that entire picture. Its violent, supersonic winds and its intricate, bipolar shape simply cannot be explained by those older, more placid models. Astronomers were confronted with a paradox. How could such a perfectly symmetrical hourglass form from what should have been a chaotic explosion? the nebula's extreme cold added another layer of contradiction. Traditional physics suggested that such a rapid expansion would generate immense friction and heat, yet here was a system that was actively becoming colder than the space around it. This forced a major revision of the rulebook. Theorists realized they had to account for two new critical variables: the staggering speed of mass loss and the phenomenally efficient cooling mechanisms at play. The old models assumed a gradual process. The boomerang demanded a hurricane. To explain this, new hypotheses are pushing the very boundaries of astrophysics. One compelling idea involves a hidden dance between two stars. If the central red giant is part of a binary system, its companion could be gravitationally channeling the outflow, funneling the stellar wind into two opposing jets and creating that iconic hourglass shape. The gravitational tug of war between the stars would also inject extra energy into the system, potentially accounting for the incredible velocity of the winds. Another frontier of explanation lies in the power of magnetism. Invisible magnetic fields generated by the dying star itself could act like a set of cosmic rails, guiding the expanding gas into those precise, symmetrical lobes with enough force and focus to drive the rapid, cooling expansion. These are not just minor tweaks to existing theories. They are fundamental reimaginings of stellar death throes. The nebula's very existence is a challenge, a cosmic gauntlet thrown down that forces science to innovate. Each failed prediction and each new, puzzling observation drives the creation of more sophisticated computer simulations. Researchers input these new variables of binary companions and powerful magnetic fields to see if their digital universes can finally birth a structure that matches the frozen beauty we see in the telescope. This process of challenge and refinement is how science truly progresses. By confronting the limits of our knowledge, we do not just solve one puzzle. We refine our understanding of universal physical laws that govern every star in the sky. The silent, frozen heart of the Boomerang Nebula is not an endpoint. It is a catalyst pushing human comprehension toward a clearer vision of cosmic evolution. To fully appreciate this theoretical battle, we need to step inside the nebula itself and see the intricate architecture that is forcing this scientific revolution. This invisible architecture is now being brought to light through a powerful fusion of art and science. Digital artists and astrophysicists work together, translating the raw numbers from telescopes into stunningly accurate three-dimensional visualizations. They take the spectral data, the velocity maps, and the temperature readings, feeding them into sophisticated software that builds a dynamic, virtual nebula. The result is not just a static image, it is an animated journey through the expanding lobes, where you can watch the supersonic winds carve their way through space. Color gradients shift from deep blues to vibrant reds, visually mapping the bone-chilling cold at the nebula's heart to the slightly warmer edges where it meets the interstellar medium. These visualizations transform abstract concepts like adiabatic cooling into an intuitive, sensory experience. You are not just told that expanding gas loses heat. You see a stream of particles billow outward and change color as its thermal energy visibly drains away. This collaborative process does more than create beautiful videos for public outreach. It is a vital scientific tool. Researchers use these same simulations to run experiments that would be impossible in reality. They can tweak the strength of the stellar winds, turn off the magnetic fields, or remove a hypothetical binary companion with the click of a button. By observing how these changes alter the virtual nebula's shape and temperature, they can test which theoretical models actually produce the intricate hourglass we observe. A simulation that fails to recreate the lopsided lobes or the profound cold is a failed hypothesis, immediately visible on screen. This iterative cycle of modeling and observation refines our understanding, offering concrete predictions for what future telescopes should see. The artistic rendering of scientific data bridges a critical gap. It allows everyone, from a researcher to a schoolchild, to grasp the complex, dynamic forces sculpting this cosmic icebox. This shared visual language deepens our collective appreciation, revealing the nebula not as a faint smudge of light, but as a violent, beautiful, and evolving system. How do these intricate local processes connect to the grandest patterns woven throughout the cosmos? This frozen hourglass is not an isolated monument. It is a single thread woven into the vast cosmic web, an immense network of galaxies, nebulae, and empty voids that gives the universe its structure. The Boomerang Nebula's very existence is shaped by forces that stretch across light years. The gentle gravitational pull from nearby stars and the subtle pressure of interstellar flows nudge its expansion, connecting its fate to the invisible currents of the galaxy. Astronomers can track its motion through space, using it as a celestial buoy to map the grand circulation of material. The same gases it now ejects will one day be swept up by those galactic flows, destined to collapse once more under gravity in a distant stellar nursery. This is the great cycle of cosmic renewal, where the death of one star provides the raw ingredients for the birth of the next. No object in the cosmos is truly alone. Each one, from the smallest dust grain to the largest nebula, is a participant in an intricate dance of matter and energy. Seeing the Boomerang Nebula as part of this grand tapestry transforms it from a distant wonder into a vital character in the story of our galaxy. It inspires a profound curiosity about the other mysteries hidden within this interconnected web. This cosmic collaboration is not limited to professional astronomers with giant telescopes. The quest to understand nebulae is a journey where anyone with passion and a modest telescope can contribute meaningfully. This collaborative spirit extends far beyond professional observatories, reaching into backyards and living rooms around the world. The story of the Boomerang Nebula is also being written by amateur astronomers and citizen scientists, whose passion and fresh eyes are making real contributions to our understanding. Using personal telescopes and powerful online platforms, everyday people are now participating directly in cosmic discovery. Projects hosted on websites like Zooniverse invite volunteers to sift through vast archives of astronomical data, classifying intricate structures within nebulae or identifying faint patterns that computer algorithms might accidentally overlook. This is not busy work. It is a fundamental part of the scientific process, a massive collaborative effort that accelerates research by adding a uniquely human capacity for pattern recognition. There are documented cases where amateurs, meticulously reviewing images of well-known objects like the Boomerang Nebula, have spotted subtle, unusual features that had previously escaped notice. These discoveries highlight a crucial truth. A diverse array of perspectives, untethered from established assumptions, can see the universe in new ways. This democratization of science breaks down traditional barriers, giving anyone with curiosity and an internet connection a chance to contribute to humanity's collective knowledge. It fosters a global community of enthusiasts, all united by a shared sense of wonder and a desire to explore. This grassroots engagement does more than just fill data gaps. It builds a foundation of public support and excitement that is essential for the next great leap. When thousands of people feel a personal connection to a distant cosmic icebox, they become advocates for the ambitious missions required to study it further, naturally paving the way for its role as a prime target for future journeys into the deep. The silent depths of the Boomerang Nebula represent a target for a journey we are not yet ready to make. While no spacecraft will voyage there in our lifetime, Its profound cold is already shaping the blueprints for future interstellar missions. Advanced propulsion concepts, from nuclear fusion engines to vast light sails, are being studied with destinations like this in mind. A probe sent to this cosmic icebox would face a voyage lasting thousands of years, a testament to human patience and long-term thinking. Upon arrival, its instruments would finally taste the nebula's gases directly, measuring their temperature and chemistry with an accuracy that is impossible from across 5,000 light-years. It would map the invisible magnetic fields and search for the subtle gravitational tug of a hidden companion star, solving mysteries we can currently only debate. This is the ultimate prize, transforming our remote observations into tangible, physical truth. Long before such a grand mission is possible, our remote eyes are growing sharper. The next generation of space telescopes, building on the legacy of Hubble and Webb, will dissect the nebula's light with even greater precision. They will hunt for the spectral signatures of complex molecules forming in the deep freeze and track the turbulent flows within its lobes in real time. Each new instrument acts as a stepping stone, providing the crucial data needed to design a probe that could one day survive the journey. The nebula serves as a perfect benchmark, a known extreme that helps engineers test the limits of sensor technology and cryogenic systems. What we learn from studying its silent storm prepares us for the other cold, dark corners of the galaxy we have yet to discover. This long arc of exploration, from a faint smudge in a telescope to a future interstellar waypoint, is a powerful lesson in perseverance. It reminds us that some of our greatest discoveries are not just about reaching a destination, but about the generations of curiosity and innovation required to begin the journey. That persistent pursuit, spanning decades and bridging continents, unlocked the nebula's frozen secrets. This was not the work of a single night or a solitary genius, but a slow, cumulative triumph of human curiosity. Astronomers battled the inherent faintness of the nebula's light, pushing their instruments to the absolute limits of sensitivity. They faced dead ends and puzzling data, where the signal was almost lost in the cosmic noise. Yet they did not surrender. They built better telescopes, forged international partnerships to share resources, and developed new analytical techniques to tease meaning from the whispers of photons collected over countless hours. Each small breakthrough, from the first temperature measurement to the mapping of its lopsided winds, was a victory earned through sheer tenacity. This story of cosmic discovery is a powerful mirror for our own lives. The obstacles we face in our personal or professional pursuits can feel as immense and daunting as the 5,000 light-year gulf to the nebula itself. The frustration of a failed experiment, a difficult project, or a personal goal that seems just out of reach can tempt us to turn back, but the nebula's journey teaches us to embrace that struggle. It shows us that profound understanding rarely arrives in a flash of instant genius. It is built piece by piece through failed hypotheses and persistent effort, fueled by the unwavering belief that there is something wondrous to be found. The universe does not give up its mysteries easily. It rewards the patient, the resilient, and the collaboratively curious. As we stand on the precipice of summarizing all we have learned from this cosmic icebox, we carry forward not just facts and figures, but a deeper lesson in the human spirit's capacity to reach for the stars, no matter how long the journey takes. Our journey through the Boomerang Nebula has unveiled a silent realm where cold itself is rewritten, a cosmic deep freeze born from a star's violent death that challenges the very laws of physics. This is far more than a record-breaking statistic. It is a profound lesson in stellar evolution, showing us how the end of a sun-like object can forge the coldest natural conditions imaginable. The nebula's intricate structure and chilling mechanisms reveal a complex cosmic ecology where matter is sculpted, enriched, and ultimately recycled to seed future generations of stars and planets. This exploration stands as a testament to human ingenuity, a triumph of technology and international collaboration that allows us to map a place we can never visit. The wonder and curiosity that brought us here are the same forces that will drive the next great discovery. What chilling cosmic secret will we unravel next? Share your thoughts on what extreme environment fascinates you most in the comments below, and subscribe to join us on our next journey into the mysteries of the cosmos. The universe is filled with silent, frozen wonders and brilliant, fiery births, all waiting for a curious mind to look up and ask the next great question.